Hi, my name is Sjoerd Smit. I'm a technical consultant at Wolfram Research Europe, and my talk is about Bayesian inference in the Wolfram language. So Bayesian inference is a very powerful way for dealing with uncertainty in your data and for fitting models to that data and comparing them. So I hope you will enjoy my presentation. My name is Sjoerd Smit. I'm from the Netherlands. I work in the UK for Wolfram Research Europe as a technical consultant. And a while ago I got interested in Bayesian inference and I started teaching myself a bit about it. Read the book by Edwin T. James. Maybe some of you will know it. Because I'm a consultant, people come with problems to me, and I thought, well, Bayesian inference would be a good thing to have in my toolbox in case someone has a problem that could be solved in a Bayesian way. But unfortunately, Mathematica doesn't have too much in the way of that, so I decided to start my own code project on GitHub and write some code, in particular, initially to implement what's called the nested sampling algorithm. So this repository, the link to that will be at the end of this talk, so if you're interested. And that's just a pretty straightforward implementation of the nested sampling algorithm. And yeah, in this talk, I want to briefly talk about what is Bayesian inference, why is it interesting and useful to have. Then I will talk about this nested sampling algorithm, and I will show you some examples of what you can do with it. Okay, so very brief introduction to Bayesian inference. Bayesian inference is based completely on conditional probabilities. So a conditional probability is just the probability that X is true given that you know that Y is true. And we pronounce that as the probability of X given Y. Now, the most important rule for calculating with conditional probabilities is called the multiplication rule, and it's the probability that X and Y are true is the probability that X is true, and then because X is then true, you have to multiply it by the probability that Y is true given that X is true. And this rule is always valid. It's not like the independence product rule. This is just a universal probability law. And because we can switch X and Y around on the left side, because the AND operator is commutative, you can also switch around these two terms on the right-hand side. And that gives you two ways to calculate the probability of X and Y, which means that you can eliminate it. And when you do that, you get Bayes' rule. So Bayes' rule gives you the probability that X is true given Y in terms of the probability that Y is true given X. So and then there are these probabilities of X and Y that you need in order to compensate for switching the conditioning around. And this is very powerful because if you're doing reasoning, you will very often encounter situations where you have to swap around what you know and what you don't know. So, and that's what Bayes' rule basically does. It allows you to swap dependencies. So let's do a really simple Bayesian inference example. We have some kind of process that produces trues and falses. We have no idea about what's behind this process, but we took some data and we found that it produced 3 falses and 9 trues. And now we have the hypothesis that these trues and falses are independent events. So we're not considering Markov chain-like models where the next event could be influenced by the previous. So for the moment, we're thinking, okay, this might be independent, and we have a probability of P that we get a true and 1 minus P that we get a false. But we don't know this parameter P, so from a Bayesian perspective, P is an unknown, something that has a probability distribution because it is unknown. So the question then is, what's the probability of this P given the fact that we have this data and the model? Because the data is the thing we have, that's right here. The model is the thing we're basically assuming for the moment. And then by using Bayes' rule, we can switch this around. So we have here a bunch of terms, and each of these terms get a name, because that makes it easier to talk about it. So the first one here, is called the likelihood. That's the probability of getting your data given the model and the p-value that you assumed at a certain value. Then here we have what's called the prior, and here we have what's called the evidence. Now this likelihood in this one is probably easiest because that's what we just learned in probability classes while we were in school. So in this case, it's just something we get from a binomial distribution. And Mathematica has a built-in function called likelihood, which allows you to just immediately get this likelihood here. And it's, 1 minus p, we got 3 of those, and we got 9 truths, so that's p to the power 9, and then we have this binomial coefficient. So that's our likelihood. Now then there is this prior. The prior is a mathematical way of stating that we don't know this value p, or at least what we believe about what we know about this value p, not having seen the data yet. That's important. So if we hadn't seen the data, then we would probably believe that the prior is just uniform. Okay, you can argue with this. Maybe it's not uniform. There might be a reason why it wouldn't be uniform. But for the moment, we have no reason to believe that it has a particular value. So it could be anywhere in the interval between 0 and 1. And then finally, there is this thing here, which is called the evidence. And the evidence you get by basically integrating the numerator, because in the end this has to be a probability distribution. This whole thing has to be a probability distribution over p. This thing here doesn't depend on p, so this is just a normalizing factor. It makes it sure that these two terms which do depend on p become a probability distribution. So the evidence is just the integral of the likelihood times the prior over p from 1 to 0, from 0 to 1, and that's 1 over 13 in this case. So now we can calculate our posterior, which is what we give the name to the left-hand side. And the posterior we can plot together with its probability distribution. So that's one of the nice things about Mathematica. You can, so this thing here is a function, and then I can convert that into a probability distribution. So in Mathematica, you can do these kind of calculations quite quickly and efficiently by using the symbolic notation and using things like probability distribution. And then we can plot it, of course. So here was our prior. So our prior is we don't know p, so it could be anywhere between 0 and 1. And then after we've seen the data, we get this kind of bumpy probability distribution. Because we've seen many more truths than falses, obviously it skews the p-value a bit above a half. And then this represents what we know about the p-value. And once we have that probability distribution, we can start asking questions like, what is the mean of this distribution? So what's the expected value of p? Or we can calculate, the mean is 5/7 apparently. We can create what's called a credible interval. This is not the same as a confidence interval, but a credible interval is basically an interval that contains 95% of this posterior. So this kind of gives you error bars on where your p-value might be. And you can ask other questions like, what's the probability that the p-value is actually still less than a half? And you can see that's 4.6%. So these are the kind of things you can do with Bayesian inference. So is there anyone who wants to quickly ask something before you move on? Okay, good. Yes. If you have a lot of data, it tends to be not very sensitive, but the prior, in a situation like this one where you have very little data, then the prior is actually very important. Like if you were throwing, and that kind of makes sense, like if you were throwing a coin and you were doing your best, then you actually have a prior that the coin is fair. That's just, you know, our everyday experience tells that this should be true. So in this case, this whole model, the whole model would probably have a quite low prior because there's no real reason why a coin should have a zero p-value, for example. Yes? Yes. Yeah, so I would say that a credible interval is much closer to our common sense of what we think of. Like a confidence interval is usually not what you think it is. That's the main problem. While a credible interval is much more intuitive. I would say it's much less easy to misinterpret.
There's a demonstration about wall versus Bayes.
Mm-hmm. Okay. Okay, so this is a simple example, and you can see that the symbolic tools in Mathematica make this quite easy to do. So in general, if we generalize this problem, then we have data, and we have a model which has some vector of unknown parameters, which I'm calling theta, and the difficulty in doing the Bayesian analysis is usually the evaluation of this evidence integral, because the likelihood you generally know. This you can compute using probability theory. The prior is something you have to think about and maybe discuss with people in order to get at a good value, because you know there is quite a bit of information in this prior. But that's you know that's a kind of model assumption, and then this integral is the thing you have to do. And in general, this integral is quite difficult. It can be very high dimensional. Like it's quite easy to end up with a model that has like 10 parameters or something, and you can't really do this numerically or analytically in general. So what are the ways to deal with this problem? Now, a very popular way to do it is by using what's called MCMC methods or Markov chain Monte Carlo methods. I'm not going into detail what those are exactly because I didn't really go down that route. But the main advantage of Markov chain Monte Carlo is that it's self-normalizing, and therefore you don't need the evidence. So actually, we only need the likelihood and the prior, and that's great. What Markov chain Monte Carlo does is it allows you to draw samples from the posterior distribution. So you have the distribution you're interested in, you can draw samples from it, and if you have enough samples, then you basically have a kind of approximation of your distribution. So it's like instead of a normal distribution, you have samples from a normal distribution, and then you use that to approximate the distribution in a discrete way. And that's what MCMC does. However, it's the main drawback is you're not computing the evidence. And the evidence is actually a very handy tool for comparing different models. I will not go into detail about that too much, but if you have two competing models that might explain the data, you need this evidence in order to assess which of the two models you should use. So if you have one model and you want to just throw that at the data, then use Markov chain Monte Carlo, no problem. If you have two models, or three, or four, or more, and you don't know what might be the best one to use, you have to compute this evidence integral, and you can't do that with MCMC, or at least not just MCMC. So we have what's called the nested sampling algorithm. The nested sampling algorithm does allow you to estimate the evidence. And let me try and explain that to you. Oh, for some reason something got deleted here somewhere. When did that happen? Is that correct? No. I think it's best if I just close the presentation and just open it, because I have no idea when that happened. Probably a slip of the finger somewhere. Oh. No. Does it work? Oh, there, yes. Oh, good catch, thanks. So I implemented the nested sampling algorithm in the package I mentioned on GitHub. And in this case, I'm using that package on data I draw from a Cauchy distribution. So Cauchy distribution is notoriously very wide. So this is it's kind of like a normal distribution, but with much heavier tails. So the parameters it has is a location and a scale parameter. In this case, 0 and 1. I generate some test data, and then I'm going to do my nested sampling algorithm. So I throw in the likelihood function, actually the log likelihood function. It's a bit easier to work with the log, which is the Cauchy distribution of the two parameters which I'm estimating. So they slot in as a function. And the data. Now my prior I specify in a general way. So I say that the first argument is a location parameter, the second argument is a scale parameter, and that automatically gives me in this code the proper priors to use for that for those parameters. And then I say, well, I want to investigate my location parameter between -10 and 10, and my scale parameter from 1 over 100 to 5. And I believe that the true values are in there somewhere, in that range. So these are some options. It's not important right now. These were the data that I drew. So you can see those 10 samples. One of them is a huge outlier, which is something that's not uncommon for Cauchy distributions. And then here is my result, which I present as a data set. And the nested sampling algorithm also created a bunch of points in the parameter space. So this is a point that has a location parameter of 0.77 and a scale parameter of 0.4. It tells me how likely that point is as a prior. It gives me the log likelihood. And it gives me weights. And these weights are what allows you to calculate the evidence, basically. So what this algorithm does, so let me give you a little plot of the problem we have. So this is the log likelihood function that I threw in here. So the likelihood of getting the data from that distribution for different location and scale parameters. And you can see that the likelihood is the highest somewhere around here. Now what the nested sampling algorithm does is it samples the prior. It generates a bunch of samples from the prior. And then you keep the best ones alive. So the best ones, in this case the best 10, I mark in red. These have the highest likelihoods out of the ones that I have right now. The brown one of the gray ones are not yet in this iteration, so I can skip ahead through the algorithm as I ran it. And then here there is the worst one, the 11th one, and this kind of gives me a likelihood boundary, which and I won't accept any new points that are worse than this one. So when I now move up through the animation, oh, this is a bit fast. Okay, so every time I generate a new point, so this one, for example, and now this one has become the worst. And every time I generate a new point, I draw from the prior, but I make sure it's better than this one. So it's within this area. And that's what allows me to do the evidence integral. Because where in normal integration, you're kind of cutting up your integration domain in slices and then you dice it up. And that won't work in high dimensions. What this algorithm does instead is it estimates the area of these kind of onion layers. So each of these contours is kind of like an onion peel. Let's stick with the cooking analogies. And you can estimate the area of this thing, and because you know the likelihood on this peel, you can estimate that particular contribution to the integral. And that's how you do the evidence integral. Yes.
So the worst and the best that you find from what perspective, from the likelihood, the points you said there, the worst and the best. How do you find which one? Or how do you define which one?
That's according to likelihood. So the ones with the highest likelihood are the best.
Is the center onion slice the first credible level or interval? Or no?
No. This is just for calculating the evidence. And what you can now actually do is that each of these points, you assign a weight, and then you get samples from your posterior distribution. So in normal Markov chain Monte Carlo, you just generate a bunch of samples, and those are all weighted the same. They all have the same weight. While in nested sampling, you generate weighted points. And these represent your posterior distribution. And we can now also plot this posterior distribution. These are the samples, and then the size of these bubbles is the weights these points got. And I can use some Mathematica functions to create instead a kind of density plot. So this is actually now my posterior function. So I can actually visualize it. I can also look at things like what's the covariance between my parameters. So for example, the location and the scale parameter have a little bit of covariance, which you can see here. It's a little bit, it's not entirely straight. And then one of the last things that's quite interesting to do is that you generate the predictive distribution. So I could, if I were to draw the next sample from my data, the 11th one, then I would like to have a probability distribution for that. And you can get a probability distribution by using, for example, maximum likelihood estimation. If you do that, you get I'm also almost out of time, but that's fine. You get one location and scale parameter, and you just use that as the distribution. What I'm here doing in this blue function, this posterior predictive function is that I actually have a lot of Cauchy distributions with different parameters, and they're all weighted according to how likely they are. And that's how I construct a new probability distribution that tells me where my next sample is going to be. So that's something you can do. And actually, because Mathematica has quite a lot of ways to generate these distributions. So for example, I used in this data set, I have here a data distribution, which is just generated from empirical distribution. So you can just throw in the points, and then you have a posterior, and you can calculate it. You can calculate with it just like in any other distribution you have in Mathematica. And finally, just as a kind of let's see, where's my repository? So as I promised, I have a GitHub repository where you can just get the code and install it and mess around with it for yourself. Yes. Yeah, that's the talk. Let's do some questions.